In this video, we're going to show you how to calculate probabilities using a number of examples. Here we go. The first example is a simple case where the probability of two events A and B are given. Also, the probability of A and B, the joint event A and B is also given. If these three probabilities are given, then we should be able to calculate the following probabilities. The first one that we can calculate is the probability of the complement of A. In order for us to do that, we use this formula. The complement of an event A, probability of A is equal to 1 minus the probability of the complement of event A. So in this case, what we can do is that we can do 1 minus the probability of A. A complement is the complement of the event A, right? So once we write this out, we can calculate probability very easily. In this case, it would be 1 minus 0.3, which is equal to 0.7. The other probability that we can calculate is the probability of A or B. Now, in order for us to calculate this probability, we would use the addition law or the additive law. To do that, probability of A or B is equal to probability of A plus the probability of B minus the overlap, because the overlap is in A as well as in B. So if we add the probability of A and probability of B separately, A and B would be double counted, and therefore we would take that one away. Now, what we can do is to just substitute this probability directly using the rule. So probability of A or B is equal to probability of A plus the probability of B minus the probability of A and B. So in this case, probability of A is 0.3, probability of B is 0.75, minus the probability of A and B, which is given to be 0.25. So if we do a quick calculation, these numbers would be equal to 0.8. The next one is also a use of the complement of an event A formula. We want to calculate the probability of the complement of A and B. So A and B is considered to be an event. So in order for us to calculate the complement of this event, we can just use this formula again. So therefore, the probability of the complement of A and B is equal to 1 minus the probability of A and B as the event. And once we write this down, the calculation will be very simple. In this case, would be 1 minus 0.25, which is equal to 0.75. Now, the next two is about the calculation of the conditional probability. To do that, we have this formula. Probability of A given B, if we know the event B, what's the probability of A? This probability is equal to the probability of A and B divided by the probability of B. So whatever is given as the event, its probability will show up in the denominator in the formula. So for us to calculate this, all we have to do is write this down. Probability of A given B is equal to probability of A and probability of B. And B, A and B as a event, divided by probability of B, because B is the event given. So if we plug in the numbers, we will have 0.25 divided by 0.75. And if you perform this calculation, that calculation will be equal to 0.33, right? So 0.75 divided by 0.25, sorry, divided by 0.75, and the answer is 0.33. And it's sufficient for us to keep only 2 decimal places. Let's do that one more time. What's the probability of B given A? So in this case, the event A is given. So probability of A would be in the bottom, right? So again, using the formula for conditional probability, this probability is equal to probability of A and B in the top, and the bottom would be probability of A because the event A is given. And therefore, again, we can just plug in the numbers. This one would be equal to 0.25 divided by 0.3. Or if you use Excel to calculate this, 0.25 divided by 0.3, which is equal to, sorry, now you know that this number is wrong because probability cannot be bigger than 1. Right? And the reason why we have this problem is because we did not put in 0.25. And once we correct that problem, this is fine now. The last one that we can do with the given probabilities is to find whether event A and B are independent. Now, how do we do that? Well, one way of doing it, and the easiest way of doing it, if you want to check whether A and B are independent, is to calculate these 2 probabilities. The first one is probability of A given B. The second one is probability of A. If these 2 probabilities are the same, that means that the probability of A knowing B is the same as not knowing B, then B has no impact on A, and therefore A and B are independent. So in order for us to check whether the 2 events are independent, we calculate these 2 probabilities and compare. If they're the same, they are independent. If they're not the same, the 2 events are not independent. So let's calculate the first one. The first one is probability of A given B. So how do we do that? Probability of A given B using the conditional probability formula is A and B divided by the probability of B, because probability of B, the event B is given, right? So the probability of B is in the denominator, okay? So how do we do that? Well, again, we plug in the numbers. Probability of A and B is equal to 0.25, and probability of B is equal to 0.75. So the answer is equal to 0.33. On the other hand, what's probability of A? Well, probability of A is actually given. We don't even have to calculate that. Probability of A is equal to 0.3. And now what we can do is to compare these 2 numbers. If they're the same, then the 2 events are independent. If these 2 numbers are not the same, then these 2 events are not independent. Well, 0.33 is not equal to 0.3. So these 2 probabilities are not the same. So therefore, the 2 events are not independent. And this is exactly what we should write down. We say, since probability of A given B is not the same as probability of A, the 2 events are not independent. If they're not the same, they're not independent. Now, it's important for us to calculate these numbers with more decimal places if it's necessary, because the 2 events are independent only when the 2 probabilities are exactly the same. So even though that they're close, if they're not the same, then we would not consider the 2 events to be independent. So in this example, we can calculate a number of probabilities once the basic probabilities of A and B are given, right? So the 3 things that you need to know is probability of A, probability of B, and then probability of A and B. And then we are able to do the number of probability calculation as well as to check whether the 2 events are independent. In the next example, we will look at how to calculate probabilities when probabilities are estimated using what we call relative frequency method. In this method, the probabilities are estimated using a sample. And so therefore, in this scenario, the concept of probabilities is the same as the concept of a percentage. So, for example, we take a sample of 250 employees in a company, and we classify these 250 employees in two ways. One way of classifying them is to see whether they have a degree or not. On the other hand, we also classify the employee in terms of their management level. So we have, in this case, either they're in management or they are in supervisory roles. So when we take the 250 people in the organization, we classify them in two ways. We will get a table like this. So for example, in this table, we have 25 employees who is at management level and have no degrees. On the other hand, there's 75 employees who are in the management level but has a degree. By the same token, we have 95 employees who's at the supervisory level, has no degrees, and then 55 employees who is in the supervisory level and has a degree. So based on this table, and later on we're going to study this table in more detail in another aspect of statistics called contingency table and chi-square analysis. This is our starting point in terms of calculating probabilities. And probability in this case, as I said, would be equivalent to percentages. So if we select an employee randomly from the company, and based on this data, this sample, can we calculate the following probabilities? And the answer is yes. We would treat the probabilities as percentages, and we kind of use the common sense. Notice that we do not need to use any formula if you apply the common sense that we're going to demonstrate to you. So let's get to it. The first probability that we want to calculate is the probability that an employee has a degree if he or she is randomly selected from the company. And this probability or percentage would be estimated using this sample. So how do we do that? Well, out of the 250 employees that is being selected, how many of them has a degree? Well, if you look at this table, there are 130 of the 250 employees has a degree. Therefore, the probability of an employee having a degree is the same as the percentage of employees that has a degree, and therefore the calculation will be just 130 divided by 250. Right. On the other hand, what is the probability that employee is at the management level if it is he or she is randomly selected from the company? Again, the way that we look at it is this. We have 250 employees in the sample. Out of the 250 employees, how many of them are at the management level? There's 100, right? And therefore, the probability of management or the percentage of employees at the management level will be equal to 100 divided by 250. All right, so this is how basic probabilities are calculated using this table. We can now look at more complicated scenarios. For example, we want to find the probability of management level and no degrees, right? So if you select an employee randomly, what is the probability that the employee is at the management level and has no degree? So how do we do that? Again, we're going to use this sample to estimate the probability. So the bottom of that is obviously 250 again, but how many of them would be at the top? So here in the fraction, well, we need to look at employee who's at the management level, right? So I'm going to use this I'm going to use this to help us. So this is the management level, right? So there's 100 of them. And how many of them has a degree? Well, how many of them has a degree? There are 130 of them. How many of them have both, right? And means both. So how many employees in the sample that is at the management level and has no degree, has no degrees here, sorry, has no degrees here. So the intersection of the two is 250, 225. So the top of this probability calculation would be 25 divided by 250, and obviously that percentage is easily calculated to be 10% or 0.1. On the other hand, we can also use the same data to calculate the probability of A or B, right? So for example, if an employee is randomly selected, what is the probability that the employee is at the management level or has a degree? So how do we do that? Well, the bottom again is equal to 250 because out of the 250 employee, how many of them is at the management level or has a degree? Well, again, we can just use this thing to help us, right? So how many of them are at management level? 100. So 100. How many of them has a degree? 130, right? So the probability would be 100 plus 130. However, if we do that, what happened? Well, when we count management, we count the 25 and 75 to get a 100. When we look at whether they have degree or not, we have 75 and 55 to form 130. So what happened? Well, the 75 has been counted twice because when we count management, we count 25 and 75. When we count degree, it's 75 and 55. So 75 is been double counted. That means it's been counted twice. So in order for us to finish off the calculation of probabilities, we should take away the 75 because this number is a double count. All right. So in a way, this is very much like how the additive law is being developed, right? So probability of A, probability of B, and then take away the double count. Okay. So again, if you want to see, you can actually use a visual aid like this to help yourself to see, right? So we can actually do this very quickly. This is 230 minus 75, or we can actually do this. Right? Why don't we just do this to save time? We can just copy the calculation and let Excel do it for us. And the answer is 0.62. Now, as I said, probability and percentage is the same concept when we use the relative frequency approach by calculating probability using a sample. Right? So I want to look at this example. The question says, I want to find the percentage of employees that do not have a degree or at the management level. So how do we do that? Percentage, probability, actually is the same thing. So let's practice. We want, first of all, employees who do not have a degree. So it's the first row. So how many of them are there? 120. Right, so 120. On the other hand, we are also looking at employee who's at the management level. So at the management level, how many of them at management level? 100. But then if we do that, what happened? Well, when we count 100, we count 25 and 75. So the 25 is counted once. When we count no degree, we count 25 and 95 to get 120. So again, 25 is being counted once. And when we count 120, it's being counted again. So 25 is the double count. The intersection is the double count. So you have to take that away. So minus 25. And then the bottom, of course, is 250. So out of the 250 employees, how many of them is at the management level? 100. How many of them has no degree? 120, and 25 being the double count. So we have to take that away. And that's how we should calculate this. And if you just copy the last part, we can actually use Excel to finish off the calculation. Right? And the calculation is 0.78. Notice that when you do this kind of calculation, having 2 decimal places would be good enough. So the next group of questions is about the calculation of conditional probabilities. And how do we know that we are calculating conditional probabilities? But there are a number of keywords that would actually show up in the question. And if you see those keywords, then you know that you are dealing with conditional probabilities. So the first one, as highlighted in red, what triggered us to think about conditional probability is the word given. So given an employee has no degrees, right? So knowing the employee has no degree, what is the probability that the employee is at the supervisory level? So given the employee has no degree, what is the probability that the employee has supervisory level, right? So if you want to write this out, what we were looking for is probability that the employees at the supervisory level, right, given the fact that the employee has no degree. So that is what we're looking for. Let me just look at this, right? So given the employee has no degree, we're looking for the probability the employee is at the supervisory level. So how do we do that? How do we apply the formula? As I said at the very beginning of this example, you can just use your common sense, right? So let's just use this to help us. And I'm going to take this away, right? So given employee has no degree, that means that we are looking at the 120 employees who has no degree. So out of the 120 employee has no degree, how many of them is at the supervisor level? Out of the 120 employees, how many of them are supervisory? 95. So therefore, the probability, the conditional probability in this case would be 95 divided by 120, right? As you can see, right, we use 120 in the denominator because of the fact that we know given an employee has no degree. So instead of looking at the 250 employees in the sample, we are looking at the 120 employees in the sample because we know given that the employee has no degree. So that this row is really our starting point in finding the probabilities that we want. So out of the 120, 95 of them is at the supervisory level. So therefore, the answer is 95 divided by 120. Okay, and again we can use Excel to do the calculation. So 95 divided by 120, of course, is equal to 0.79, right? So again, it's useful just to round it up to 2 decimal places. So let's practice one more time. If you look at this question, if an employee is at the supervisory level, what is the probability that the employee has no degree? So if an employee is at the supervisory level, so given, right, if as the same as given the employee is at the supervisory level, right? So we look at all the employees at the supervisor level, that's 150 of them. Out of the 150 of them, how many of them has no degree? Well, 95 of them has no degree. So the probability or the percentage is equal to 95 divided by 150. Okay? Why is 95 divided by 160 one more time? Because if an employee is at the supervisory level, given the employees at the supervisory level, there's 150 of them, and out of the 150 employees who is at the supervisory level, how many of them has no degree? 95 of them has no degree, right? So therefore the probability is 95 divided by 150. Unless you have to do a comparison, a lot of times given out this answer would be would be satisfactory. So if you want to convert this number into decimal places, of course you can. But as I said, you can actually just leave it in at the fraction, right? So this is 0.63. Now, the last thing we can do, now that we know how to calculate conditional probabilities, is to check whether two events are independent. So in this question, we ask, are the events management and has a degree independent? Well, the question is not too difficult to answer, right? Why? Because all we have to do is to calculate the conditional probability, management, one of the UN, given the other UN has a degree. Now, the order is not important as long as you just calculate the probability properly. So that's the first probability. The second probability, of course, is just management, right? Knowing the employee has no degree, does it help to update the probabilities? Well, if the two probabilities are the same, that means no. In that case, they are independent. So the UNA management has no bearing on has a degree or vice versa. On the other hand, if they are not the same, that means knowing that the fact that the employee has a degree actually changed the probability. Well, that means the two UNs are dependent, are not independent, so therefore dependent. So how do we know the two UNs are independent? We calculate these two types of probability and we're going to compare them. Right, so now let's calculate the first one. The first one is, given the employee has a degree, what is the probability that the employee is at the management level? So how do we do that? Well, given the employee has a degree, so we're looking at these 130 employees who has a degree. And out of that, how many of them are in management level? 75. So this probability is equal to 75 divided by 130. And because of the fact that we are doing a comparison, so what we need to do is we need to calculate it out, right? So we do 75 divided by 130, because that makes it easier for us to look at the numbers and do a comparison. The second one is just the probability of management. And how do we do that? Well, all you have to do is, my typing is terrible, as you can see. Right, let me just fix this. How do we calculate probability management? Let's practice. How many of them are in management? There are 100 of them in management out of 250. So the probability that an employee is at the management level is equal to 100 divided by 250. And again, because of the fact that we need to do the comparison, so what we should do is we should actually use Excel or use a calculator to calculate this number. Right? So 100 divided by 250, and the answer is 0.4. So the question is, are they independent? That means, are these two probabilities the same? If they're the same, they're independent. If they're not the same, they're not independent, right? So that these two numbers are not the same, so therefore these two events are not independent. So that's why of the conclusion, we say since probability of management given as a degree is not the same as the unconditional one. Right? So knowing the employee has a degree actually changed the probability of management in some way. So therefore, the two events are not independent. So this is how you evaluate two events and see whether the two events are independent or not, by always calculating the conditional probability and the unconditional probability. And you don't have to check two pairs, only have to check one pair of probabilities. and it will be good enough. So in these two examples, we have seen how probabilities can be calculated using the formula, or we can actually just use the common sense. If the data is summarized in a contingency table and we're using the relative frequency approach to calculate probabilities. The last example that I want to show you, of course, is in relation to the Bayes theorem. Now, the Bayes theorem seems to be very complicated, and here is an example of the Bayes theorem when we have two events. In order for us to apply the Bayes theorem, we need to calculate all these probability, and we need to be able to identify them properly. So an alternative in doing the Bayes theorem is actually to draw a probability tree, and based on the probability tree, we can actually calculate the probability quite easily. So to do that, we're going to use an example. Suppose in this example, 3% of babies in a remote community has certain blood condition. So let A be the event that is a baby had the condition. So either a baby in the community has the condition or do not has the condition. So probability of A is equal to 0.3 because 3% of the baby has a condition. If 3% of the baby has the condition, then 1 minus 0.03, which is 0.97, is the probability that they do not have a condition. Okay? So how do we use it? Well, we first draw the first two branches of the tree, right? So there are two branches because it's either A or the complement of A. So either the baby has a condition or the baby do not have a condition. And the probability that the baby has a condition is 0.03. The probability that the baby had no condition is 0.97. Now let's look at the next level in the tree. Based on research result, if a baby has the condition, the test correctly identify the baby as having the condition 90% of the time. On the other hand, if the baby does not have the condition, the test incorrectly identify the baby as having a condition 12% of the time. So how do we use this information to draw the tree? Well, if let B be the event that the medical test identify the baby of having the condition, we can now draw this line and this line, right? So B means the baby is being identified of having a condition. So this branch, A and B, means that the baby has a condition and the test identify the baby of having a condition. And the probability of that is equal to 0.9, which is obviously given. Now, once we draw this branch, then we can immediately draw this branch as well, because this is B complement. B complement represents the fact that the baby has a condition, but according to the test, the baby does not have the condition. And we can also find the probability. Why? Because these two probabilities should be adding up to 1. So if this is 0.9, this is 0.1. Right? So this branch is complete based on that. Now let's look at the lower branch. The lower branch says if the baby does not have the condition, that means in this branch, the test incorrectly identified the baby as having the condition 12% of the time. The test identify the baby has the condition is 0.12. So this is the third branch from here. And once we complete this branch, then we can also write down the branch here. Now the branch is the baby has no condition, and according to the test, is also identified that the baby has no condition. And the probability of that would be 0.88. Why? Because the two probabilities should add up to 1. So this is 0.88. So once we put down all the probabilities, then this probability tree is complete. Once the tree is complete, what we can do is to calculate what we call the joint probability. That means the probability of this branch, the probability of this branch, the probability of this branch, and the probability of this branch. Now, to calculate this probability, all you have to do is to multiply them, right? So the probability of the first branch is 0.03 times 0.9, which is equal to 0.027. The second one is 0.03 times 0.1, which is equal to, this is a mistake, is 0.003. Now, fortunately, we are not going to use this branch, so the mistake here doesn't affect us. For this branch, it would be 0.97 times 0.12, which is equal to 0.1164. And for the probability of the last branch would be 0.97 times 0.88, which is equal to 0.8536. So this probability represents the case where the baby has the condition and the test identify the baby of having the condition. On the other hand, the third branch would be the baby do not have the condition, but according to the test, the baby is identified as having the condition. And the probability of that is 0.1164. So now that we calculated 4 probabilities, how can we then answer the question? The question is this: if a baby is identified by the medical test of having the condition, what is the probability that he or she does not have the condition? Right? So that's like in reality, you don't know which baby has the condition or not. You only know the percentage, but we always know the result of the test because we administered the test. So now that we administer the test, we can now calculate to see whether the probability that she has a condition or not as the diagnostic of the test. So how do we calculate this probability, which is kind of in reverse? Well, all we have to do is, first of all, identify the branches that show the medical test of the test is showing the baby has a condition. So in this, going back to the probability tree, which 2 branches show the baby is having the condition? Well, this branch and this branch. And the probability for these 2 branches is 0.027 and 0.1164. So we're going to focus on these 2 probability. Out of this probability, which one would tell us the baby in fact has no condition? Well, this branch, right? Because this branch go back to a complement which says the baby has no conditions. So therefore, the probability that we want is very simple. You take this probability, divide by the all possible situation where the baby is tested positive, which is this one and this one. So therefore, the probability of that is 0.1164, right? The branch that we want, right? Testing false positive, but the baby has no condition, right? Versus the 2 possibility when tests are is positive, right? So 1164 divided by the total of these 2 branches. And the answer in this case is 0.812. So instead of using this complicated formula, you can just use the kind of common sense that we can apply to this probability tree and arrive at the correct probabilities. So that's it for the basic calculation using the 3 different examples. And I hope that you enjoy it, and we will see you next time. Bye for now.